The Anova, or analysis of variance, is a theory-based test for comparing multiple means. Technically, it could be used to compare two means, but typically people will use a two-sample t-test for that and save an Anova for comparing three or more means. The test statistic for the Anova is called the F statistic, which is related to the MAD statistic that we saw when using the multiple means applet, but it's a little bit different. The validity conditions for the Anova are in two parts. The first part of the validity conditions are the same as what we saw for a two-sample t-test. We either need the response variable to have a symmetric distribution in all of the groups, or we need all of the groups to have a sample size of at least 20 and have the response variable not be strongly skewed. In addition to that condition, we need the largest standard deviation to not be more than 2 times the smallest standard deviation. In other words, we need all the groups to have similar amounts of variability. The key idea behind the Anova is we're trying to answer the question, could the data have come from 3 populations with the same mean? That would be the null hypothesis. To do this, we compare the between group variability to the within group variability. For example, in the picture shown on top, we have 3 groups with different means. And the between group variability, that is the distance between the red circles, the green diamonds, and the blue stars, is much higher than the variability within each group, that is the distance between any 2 red circles, or between any 2 green diamonds. In contrast, the picture on the bottom shows groups that could plausibly have the same mean. And we can see that because the amount of variability or spread between the red circles, the green diamonds, and the blue stars is similar to the amount of variability between any 2 shapes of the same type. The Anova F statistic is the ratio of the between group variability divided by the within group variability. If the F statistic is large, that indicates that different groups are spread out much farther than any one group is spread out within itself. So large values of the F statistic indicate that there's strong evidence against the null hypothesis. This is similar to what we saw with the MAD statistic, that larger values indicate stronger evidence against the null hypothesis. Another way of writing the between group variability is to call it the variation due to the factor or the treatment, the explanatory variable. And another way of writing the within group variability is the variation due to error. This doesn't mean error like you're making a mistake. This just means error due to random chance, due to sampling variation of who we happen to sample. So the numerator is telling us the variation due to the explanatory variable, and the denominator is telling us the variation due to random chance. Let's try using an Anova to analyze this study. Researchers randomly assigned kids to learn to read using one of 3 methods. They measured the kids' improvement in reading comprehension scores. Take a moment to think about what the null and alternative hypotheses would be for this study. We could write the null hypothesis in symbols as mu sub 1 equals mu sub 2 equals mu sub 3. Where mu sub 1 is the mean improvement in reading scores among all kids in the population who learn using method 1, and similarly for mu sub 2 and mu sub 3. The alternative hypothesis would be that the mean improvement in reading scores is different for at least one of the methods. We could also phrase the null and alternative hypotheses in terms of association between the variables, improvement in reading comprehension score, and method used to learn. Here are some box plots and summary statistics of the data. Take a moment to think about whether an Anova is appropriate. Here, the sample sizes in all of the groups are small, 5, 6, and 5, so much less than 20. But the box plots show that the samples do seem to be symmetric, so the first criterion in the validity conditions is satisfied. For the second part of the validity conditions, the largest standard deviation is 2.39 and the smallest is 1.58. 2 times 1.58, the smallest standard deviation, is 3.16. So the largest standard deviation, 2.39, is less than 2 times the smallest standard deviation. So the second validity condition is satisfied also. That means that yes, an Anova is appropriate. To do an Anova on your TI-83 or TI-84 calculator, you can go to Stat and then Edit, and then enter the data in lists L1, L2, L3, and as many lists as you need to cover all of the groups of the data. Then go to Stat and Tests and choose Anova, and enter in the names of the lists where you stored the data, separated by commas. The output of the Anova gives you the value F. That's the F statistic, the test statistic that we're finding the probability of being at least as extreme as. P is the p-value. And then there are sections labeled factor and error. Factor is describing the amount of variability due to the treatment or explanatory variable, and the error section is describing the variability due to random chance. So don't worry if you see the word error on your screen. It's not saying that there was a problem, it's just describing the variability due to random chance. In this case, we get a small p-value. So our conclusion would be there is enough evidence to claim that the mean improvement in reading scores in the population is different for at least one of the teaching methods. Entering the data into the lists on your calculator can get kind of tedious. So if you have a large data set, it's often better to conduct the Anova in the multiple means applet or in Minitab. Here's what the output for the reading comprehension study looks like in Minitab. You see we still have lines for the factor and error telling us about the variability due to the explanatory variable and due to random chance. And on the far right, we have the p-value, which is usually the main thing you want to focus on.